Hi everybody, I'm Greg Kiar, and I'm going to be talking to you today about Brainhack 101, which is kind of a beginner's guide to computational neuroscience, mostly looking at some of the tools that will help you really get started later on. Previously, when I've given this lecture, I've been working with people kind of face-to-face in a workshop style, and we've taken about 3 or 4 hours and really kind of dug in and worked on all these things, kind of did a little bit of talking about them, and then actually practiced. So I'm going to try, in the interest of keeping this short, I'm going to try and just kind of gloss over each of these topics, provide you with links so that you can kind of do more reading on your own, and give you little practices or little practical things that you should try and do on your own time. Maybe pause the video and work on them just to make sure that you actually are getting acquainted with these tools. So again, we're going to talk about just a little bit of why what I'm going to talk about matters, why you should care, talk about some tools that'll help, and then at the end I'll give you guys again some quote-unquote homework that will help you practice all these skills. Perfect. So, as you all probably know, there's lots of data and lots of tools popping up in neuroscience, with projects such as the Human Connectome Project, the UK Biobank, the CORE Initiative, the MNI Data Sharing Initiative, countless others. We are starting to get to a point where data collection is no longer the bottleneck in neuroscience research. And neither is tool development. We have tons of different tools, whether they're foundational tools that are leveraged in lots of other pipelines, such as FSL, ANTS, AFNI, these types of tools that do registrations and other types of analysis that a lot of other pipelines leverage, or whether they're specific pipelines, such as maybe CPAC or fMRI prep or other things like that. There are lots of tools, lots of data, and in order to use them effectively together, there's a need for people to learn how to code. So what we want to do is process this data, perform robust analyses so that our claims and findings can be generalized, learn and communicate our results. So in other words, come to like the root message that we're trying to communicate, and then communicate that effectively. Share our methods, and enable others to build upon our work. And in a way, these 5 bullets are pretty much science in general. You want to collect and process data, analyze that data in a way that's generalizable and robust and stable. Figure out the point of what you've actually found. What is the important finding, the takeaway message? Communicate that. Share how you got there, and have your work be foundational for other people. So really, that's all we're trying to do here. But it's not quite so easy, because often code can be really unorganized and hard to use. And tools even give different answers across versions. So say you're using version 1 of a tool versus version 1.1. You might get different answers, and unfortunately, it's quite common that you do get slightly different answers and sometimes significantly different answers. These differences can also be amplified across operating systems. So even the same versions of the tools or pipelines on different operating systems, say CentOS 6 versus CentOS 7, will give you different answers. And this makes reproducing analyses very difficult, and does in fact sound like it requires a fair bit of programming. But thankfully, there are tools to help with each of these problems, and well, we're in Brainhack 101, so we can learn how to tackle all these problems. So to try and summarize what I've just been saying, let's break this down into 3 major challenges. Code is often unorganized, unversioned, and undocumented is our first one. The second one is that the installation is difficult for tools, and operating systems can often cause differences. So this goes also along with versioning, because it's operating system versioning, let's say. And then communicating and reproducing analyses is also often difficult or incomplete. So for each of these challenges, what we're going to do is talk a bit about the problem, describe the qualities we want in the solution, learn about tools that satisfy these qualities, and then I'll give you guys a practice to play. So the first challenge, as I mentioned, is code sharing. So there's several questions that come to mind when you're thinking about code sharing. First of all, how do you share it? What happens when you make changes? What if there are bugs in your code, and how do you get credit? So all of these are questions that you may ask when you're thinking about sharing your code and making it open. And really, there's two major tools that can help you kind of get there. And so what we're going to, our proposed solution will be to host the code in the cloud. We're going to version control and track changes. We'll have a mechanism for receiving feedback and the possibility of attaching a digital object identifier, or DOI, so that people can cite us. So as I mentioned, there's two major tools that'll help this. GitHub will do most of the heavy lifting, and Zenodo will give us a DOI as well. So for those unfamiliar with GitHub, it has a great getting started guide, and I'm not going to try and replicate that, but simply I'll show that it's an ethical choice for actually solving the concerns we have. So again, please do click on the Getting Started guide if you want to learn more, and they've got plenty of tutorials that are quite useful for beginners. So as I mentioned, we want to have cloud-hosted code. So GitHub doesn't actually let me embed their page in another web page, so this is kind of a cheating version to view my repository. But as you can see here, there's files, including like index.html, images, CSS. This happens to actually be the GitHub repo that are these slides themselves. So this is online, and you can go and you can interact with any of the files you want. You can look at them, you can make changes, you can copy them, you can download them, whatever. And all you have to do as someone who finds it on the internet is use them in accordance to whatever the license is that's in the repository. And so there's a few different types of licenses, well, many types of licenses, and in particular, we in our community, we generally are focusing on open access licenses, and there's three major ones that people talk about. We have the Apache 2 license, we have the GNU public license, and we have the MIT license. And they're very similar in their root, and you should really Google them if you want to know which one, or pick a license for your project. The essential difference is that GNU public license, or GPL, is the most permissive, and a user can do anything with your code. Essentially, they can download it, they can change it, they can redistribute it, with changes, and that's all fine. The MIT license is slightly less permissive, and the Apache license is still slightly less permissive, and they still allow use and allow modifying code and things like that, and all of them require attributing the original authors. The Apache 2 license in particular just provides patent protection. So in other words, if a patent is eventually derived from your code and you wrote the code first, you're protected there. And if anybody listening to this believes that to be incorrect, please just send a pull request to this repo and correct me, because I'm by no means a licensing expert. But of course, Googling difference between open source licenses will get you an answer. So great. So we know that now we can host code publicly. So we want to track versions and track changes. Excuse me. So the way updating code works in GitHub is you make a change to a file, and what GitHub stores is not the entire new file itself, but only the changes. So say I change the title of this slide from versions and changes to versions and with an ampersand changes. So what would actually happen in GitHub if I save this file and committed it? A commit is essentially a save in GitHub, and uploaded it, the entire file wouldn't be duplicated, but simply this one line would be deleted, and this one line would be re-added with the ampersand in the place of the and. So that's a way that GitHub efficiently stores data, so that you don't have massive blobs of data as your repository grows, as you work on it more, but you're still not losing any information. So so the way that these commits work is you essentially attach a message to them. So I added a gitignore file, I added a GitHub guide link, GitHub slides, minor progress. You can encode emojis, which is fun and often unnecessary. And then on the page, you can actually browse through commits, and you can go back to any particular change and see the state of the repository there. So in line with this is you can actually make versions as well. So you can attach a version to a commit, and it'll freeze the repository at a given point and all the commits before that point. So that say you make a publication and you have a pipeline version 0.6 of your pipeline. You save that version in your repository, you publish your paper, and then a few months later you come up with this brand new technique for visualizing your results that's way cleaner, way more beautiful, more interactive, whatever. And so now it's version 0.7. So somebody could go and just install your code and run it, and they might get answers that are the same, but the visualizations they're expecting are quite a lot different from what you published. However, if they went and installed specifically version 0.6 instead of 0.7, they'd be able to get the exact same results as what you had. So this versioning goes a long way towards both reproducibility and, more simply, repeatability, being able to run an analysis, run a piece of code, and get the same expected output. So feedback for bugs is another really big pro of GitHub. There's something called GitHub issues. So if you go to whatever repository it is, if you can see in the bottom of the screen there, this is the Brainhack 101 repo, the organization brainhack101.github.io repo, in other words, this website, /issues. So if you go to any repo /issues, what you get is a page where you're able to open new issues and browse existing, both open and closed issues. So what this allows people to do is not only contribute and offer suggestions, improvements, modifications, bug fixes, what have you, but it enables people to browse what other people have contributed as well. So for instance, say there's a bug that one person encounters, you help them solve it, and another person encounters it as well. They can go to the issue page, which is Google indexed, find the issue, and save both you the trouble of having to answer it and them the trouble of having to post the same question. So the GitHub issue tracker is very useful, and even internally for project management, they have project boards attached to the issues, which are very useful. So finally, Zenodo, NDMG just happens to be a project of mine. Zenodo allows you to attach a DOI to a repo, again, requiring a specific version. So this one happens to be 0026. And what you end up getting is an actual DOI, a fully registered DOI that you can provide to users so that they can cite your tool. And this is a great way for getting citations pre-publication of an actual paper. Cool. So that was the short version of GitHub and Zenodo. So what I want you to do is quickly pause the video, create a repository, add a license, add code, create a version, add an issue, add a hook for Zenodo, and kind of go through these motions. Of course, message me on the Brainhack Slack, which I believe you've all been introduced to. If not, then, well, I think you can just Google Brainhack Slack and you'll find it. But message me there if you have any questions, and once you're done, you can unpause this video and go on to the next section. So the second challenge we wanted to talk about was tool portability. So how can you make pipelines and tools work across operating systems? How can their installation be easy? And how can it be clear what version you're using so that you can get the same results as somebody else? So we want tools to be agnostic to operating systems as much as possible, them to have one-click installation, and for there to be version control. To solve all these things. All of these features are pretty much direct extensions of what we just said as concerns. So tools that'll help are primarily Docker, and then Circle CI and Travis CI. I'm going to mention here, but we won't actually dive in too much. Continuous integration, or CI, are resources that build and compile instruction sets that you provide with them every time you push a new commit or a new version to GitHub. And this can be really valuable. So say you're developing a tool, you have a bunch of tests, and what you want to do is every time you push a new version, you want to update a public image or make a new release or what have you, so that users can get the most recent version of your tool. Well, you of course don't want to be pushing things with bugs, so you can have CI run all the tests for you, and on successful completion of the tests, then publish your results to whatever repository you want people to look at. So whether it's, say it's a Python package, putting it on PyPy, say it's a Docker Hub image, which I'll explain more in a minute, put it on Docker Hub or Singularity Hub or what have you. So continuous integration, again, I'm not really going to talk about, but I strongly encourage you to look into. So again, Docker has a great getting started guide. I'm going to say that at least one more time when I talk about Jupyter. I'm not going to be trying to reproduce any of these, but again, simply look at these the features that we talked about and show Docker's efficacy for what we want to do. So OS agnostic. So Docker containers are essentially, well, containers. So you have images, containers, and these are not to be confused with virtual machines. So this is, again, just simply the Docker help page where virtual machines sit on top of a hypervisor and have a guest operating system. Containers sit naturally on the host OS. So it's a slightly different organization, and if you're not a computer scientist, this may not be obvious to you, but for those people who've used like VirtualBox as an example, you can think of Docker as a lighter weight, more portable version of this. And all operating systems, including Windows, well, all with an asterisk, Windows, Linux, and Mac can run Docker. I'm not sure about any of the bleeding edge versions of Linux, but CentOS, Ubuntu, some other Debians can run Docker just fine. So one-click install. Another nice thing about Docker containers is that you can essentially launch them with one line. So you can do Docker run hello world. And what this will do is it'll launch some pipeline or application that is simply called hello world, and it does something. So if you are using Docker and you package your tool into something that we just were looking at, a Docker image, what you can do is have Docker run Greg's tool or what have you. And then a user will be able to do the same thing, and it'll run just as it had on your system and your machine, allowing them to not necessarily have to install it on their host system, but effectively still be able to use it. So with Docker Hub, with Docker there is Docker Hub, much like GitHub, where you can have different organizations, and you can post your images, have version control, have descriptions, things like that. So again, here happens to be a repository of mine with Docker images that are all tagged, and excuse me, and then a user is able to pull down a specific version and run my tool. So a really nice way that the continuous integration is used is essentially to run tests and to push images. So here on the right here, I show Travis CI, which is one of the two most popular, at least in my circles, most popular continuous integration tools. And on the left we have Circle CI, which is the other. So if you were to click here, what you'd see is, or bring you to the Circle CI's main pages, and this is, I believe, for my particular tool, Bids Nutmeg, which I showed in the previous slide. And what it does is it builds my Docker image. It runs my Docker image. It tests running some data through my pipeline, and given that it passes, then it pushes the new version to Docker Hub. Whereas on this case, it's a Python package we're testing, so it runs my code on, as you see, several different versions of Python, and given that all of them pass, it again runs, or it pushes my code to Python. So continuous integration is a really nice way to ensure you don't forget the testing step before publishing your tools. So again, this is the time when I'll ask you to hop back up to the top here, click on the guide, bounce around, and do some practicing. So you want to install Docker on your machine, run their Hello World account, or Hello World image, sorry, create a Docker Hub account, make a very simple Docker file. Again, their help documentation is very comprehensive. Build your image, push your first one to Docker Hub and push your Docker file to GitHub. Whereas a Docker file, which again you will learn from the documentation, a Docker file is essentially a small set of instructions that builds a Docker image. And then a bonus would be linking this with a continuous integration app as well to test it. So if you need examples for this, again, please send me a note. There should be at the end of this, at the end of these slides, there's a link to a page with a bunch of more links. So I have examples of all this there, and I believe even in the Brainhack 101 repo, or organization rather, there's a repo with a bunch of examples. So again, please don't hesitate to reach out if you have questions. But now's I think a good time to pause the video and play. All right. So the third and final challenge we're going to be talking about is performing reproducible analyses. So it's very important that in science that your findings are, well, reproducible, or at least the principles therein are. Otherwise, if you're not reproducible or generalizable, your science isn't very impactful because it isn't able to influence other science. So how can we make these analyses reproducible? How can you communicate it clearly? And how can you demonstrate that your data or that your analysis is robust? So we want a simple execution interface, so a very simple way to launch our code and look at it. We want text annotation of our analyses. So in other words, to be able to have inline documentation accompanying our code, and interactive widgets so that people can not only run our code, but be able to tweak little parameters without actually having to know anything about our program, but simply play with, like, say, sliders or drag down menus or what have you in a web interface. So the major tool we're going to be talking about here is Jupyter and some Jupyter widgets. And there's many Jupyter widgets libraries. I'm simply going with the IPython native widgets, but there's many third-party ones as well. So as I promised, one more time, Jupyter has a very good getting started guide, and same with the widget guide. So please look there for comprehensive documentation on how to use this tool. But essentially what Jupyter is a web platform for interacting with, running, and documenting code. So again, you simply launch a Jupyter page in a web browser, and inside of that you're able to write markdown stylized text, you're able to embed latex, say like equations, as well as code. And you're able to run the code blocks, embed the figures, and interact with it all in one place. And this is really nice because what it allows is that readers or users to look at your code and interact with your code and your figures without actually leaving the comfort of a web browser. So, as I promised, this is an execution interface. So what you have here is this Jupyter heading, the title of your notebook, and this is kind of, if you ever see this interface, you know that you are in a notebook if you've seen this before, even if you didn't necessarily know what it is. So there's a bunch of menus and things you can do, including like running code, stopping the code that's running, resetting your kernel, moving a cell up and down, changing the style of a code block or what have you. But essentially what you're able to do is, again, say that right now we're using a package called pandas. This is just a Jupyter example from their website. We have a data frame and we make a plot with a widget. So then if this were a web page and not just a screenshot I've taken, I'd be able to actually interact with this figure. And again, this is all from within inside of a web browser, so you don't have to mess around with terminals or anything like that. Now, you can do text annotations as well. So as I said, you can do markdown stylized text. Markdown is the same formatting engine that's used inside of GitHub text. If you have like GitHub README files where you see headers or strike-throughs or bolds and italics, all those things, you can have monospace text, fixed width text and things like that. You can have icons, you can embed LaTeX equations, what have you. Again, this enables you to do documentation in line with your code. And finally, you can have a more comprehensive set of widgets than even in the top plot. So here's the plot that I made at one point where you're trying to show a bunch of data. It happens to be synapses detected from electron microscopy volumes. You can set thresholds either by a slider or a text box. You can scale the transparency. You can scale the size of each of the blocks. You can change the color, the title, and it'll print you some summary about your data when you're visualizing it. So again, this is a really nice way that you can provide a plot with, say, default parameters that you used in your analysis. But then you can enable users to actually mess around, change parameters, and see how stable or representative your choices actually were. So again, this section's practical will be to install Jupyter widgets, launch a server, create a notebook, and essentially make a plot using a Jupyter widget in your notebook, and of course, pushing this back to GitHub as well. So again, you can pause here, do the practical, and resume in a few minutes whenever you're done. So what we've done today is look at kind of accomplishing a lot of the low-hanging fruit towards doing computational neuroscience in an open and reproducible way. We've learned how to put code on GitHub. We've learned how to create Docker files and Docker images, pushing them to Docker Hub, potentially doing continuous integration to test our code, as well as doing interactive plotting and performing accessible analyses through the use of Jupyter and Jupyter widgets. So what you're going to do now is, essentially as your practical, is do all that again, start from scratch, make yourself a new GitHub repo, put data somewhere public, where, I mean, if the data is already hosted somewhere else, that's probably better, because as a rule of, thumb, you shouldn't put data in GitHub repos. GitHub is better for smaller non-binary files. And then, so you want to have data somewhere public, set up your environment in Docker file, and do some analysis in Jupyter. And again, what this allows you to do is give somebody a link to that GitHub repo where you did all of this, a link to your Docker file, and they will be able to, with minimal effort, reproduce exactly what you did, regardless of if they have a brand new computer or one that's polluted by all of their packages and broken versions of things. So, as I mentioned, there is a GitHub repository called Scratch the Dura in the Brainhack 101 organization. Again, you can see the link at the bottom here, github.com/brainhack101/scratch-the-dura. Sorry for my bad brain pun. And you can play there, see what examples exist, and use that maybe as a little bit of inspiration. So thank you very much for your patience. Again, you can hit me up pretty much anywhere with the handle gcare for questions, including the Brainhack Slack, GitHub, Twitter, what have you. And happy hacking. Thanks, guys.